Carbon dioxide or CO2 is one of the most important greenhouse gases released by human activity. As you all are aware, it comes from power plants, refineries, chemical kilns, and almost every heavy industry that still depends on fossil fuels. Now let's be realistic. We can't shut all of these down overnight, but what we can do is capture the carbon before it reaches the atmosphere. That's where carbon capture technologies comes in, often grouped under carbon capture and storage or CCS. In this video, I'll walk you through the main carbon capture processes used today. No heavy equations, no unnecessary jargons, just clear explanation and real engineering logic. Let's start with the big picture. Every carbon capture system answers one simple question. At what stage do we remove CO2? There are three main answers to it. In pre-combustion capture, carbon is removed before the fuel is burned. The process produces hydrogen-rich fuel that when burned mainly generates water and heat. Secondly, post-combustion capture. This is the most familiar approach. Fuel is burned in air just like a conventional power plant, and CO2 is removed after combustion from the exhaust gases. Whereas in oxy-fuel combustion, nitrogen is removed from the air first and fuel is burned in nearly pure oxygen. This gives an exhaust stream already rich in CO2. The real differences between these systems comes down to CO2 concentration, gas composition, and how much energy it takes to separate the CO2. In pre-combustion capture, instead of burning fuel first and worrying about the CO2 later, we deal with the carbon upfront. Let's see how that works. Imagine taking coal or biomass and not burning it directly. Instead, you heat it with a controlled amount of oxygen or steam. The fuel doesn't fully combust. It breaks down into a gas mixture called syngas. Syngas mainly contains of hydrogen, carbon monoxide, and carbon dioxide. Before anything else happens, impurities like ash and sulfur are removed to protect downstream equipment. Now comes the clever part. The gas passes through a water gas shift reactor where carbon monoxide reacts with steam and turns into more hydrogen and more CO2. This step is crucial because hydrogen production increases whereas CO2 concentration also goes up, and higher CO2 concentration means easier capture. Special solvents are then used to separate CO2 from hydrogen. The hydrogen becomes a clean fuel, and the CO2 is compressed and stored deep underground. And here's an interesting twist. If biomass is used as a fuel, this process can actually lead to a net negative emissions. The downside? These systems are expensive, complex, and best suited for large-scale plants. They are very difficult to retrofit into existing facilities. Now let's look at the more compact pre-combustion options. Autothermal reforming or ATR. ATR combines two reactions in one unit. Partial oxidation uses a small amount of oxygen to generate heat. That heat then drives steam reforming, all in a self-balanced process. Once again, the syngas goes through a water gas shift reaction, boosting hydrogen CO2 levels. The CO2 is separated using solvents and hydrogen is recovered as fuel. ATR systems are compact, efficient, and well suited for blue hydrogen production. The main drawbacks are they require high purity oxygen, which comes from an air separation unit, and that consumes a lot of energy. Let's look at steam methane reforming or SMR. SMR is the most established hydrogen production technology in the world. Natural gas reacts with steam over a nickel-based catalyst at high temperature, producing syngas. After the water-gas shift reaction, CO2 concentration increases and is separated using chemical absorption, typically amines, or physical solvents at high pressure. SMR produces a very pure hydrogen, but there's a catch. Because it relies on fossil fuel, methane leaks must be tightly controlled and the process consumes a lot of energy. That makes CO2 capture less efficient unless the system is very well designed. So far, we looked at ways to remove carbon before combustion. Now, let's change the question. What if we change the combustion process itself? That's exactly what oxy-fuel combustion does. In normal combustion, fuel burns in air, but air is mostly nitrogen. The nitrogen doesn't help combustion, but it does dilute exhaust gases, making CO2 harder to capture. Oxy-fuel combustion removes nitrogen before combustion. Fuel is burned in nearly pure oxygen, while nitrogen gone, the exhaust gases contain mostly CO2 and water vapor. Once the water is condensed, what's left is a CO2 stream that can exceed 90% purity. That makes CO2 capture more simpler. The trade-off? Producing pure oxygen requires a lot of energy. Because of that, oxy-fuel systems are still mainly at pilot or demonstration scale. Finally, let's look at the most widely deployed approach today: post-combustion capture. Post-combustion capture treats the exhaust gases after fuel has already been burned. The flue gas is cooled and passed through a liquid solvent, usually an amine. CO2 reacts chemically with the solvent and is absorbed. The solvent is then heated in a stripper, releasing the CO2. The CO2 is captured, compressed, and stored. The solvent is reused over and over again. This method achieves high capture efficiency and can be retrofitted to existing plants. But there's a downside. Heating the solvent requires a lot of energy, creating a significant energy penalty. It produces heat while naturally capturing CO2. Instead of burning fuel directly in air, CLC uses a solid metal oxide to transfer oxygen. In the air reactor, the metal reacts with oxygen from the air without mixing nitrogen and the fuel. In the fuel reactor, the metal oxide releases oxygen to burn the fuel, producing heat, CO2, and water. The reduced metal is then sent back to the air reactor and the cycle continues. Because nitrogen never mixes with the fuel, the exhaust after water removal is nearly pure CO2. CLC avoids the need for solvent scrubbing or pure oxygen combustion, but challenges remain, including oxygen carrier durability, reactor scale-up, and solid circulation control. Carbon capture isn't a single solution, it's a portfolio of technologies. Initially, pre-combustion, post-combustion, and oxy-fuel systems were seen as separate solutions for different industries. But today, these technologies are often combined and integrated to deliver a more efficient and practical carbon capture solution. Understanding the chemistry, thermodynamics, and engineering behind these processes is essential if you want to decarbonize heavy industry. Carbon capture won't replace renewables, but it will help bridge the gap to a low carbon future. Thank you for watching.